Now we're going to get into the ramifications of this three-cell model, and particularly the polar cell, and its impact on what you know as the jet streams. So the jet streams are literally rivers of very fast-moving air in the upper atmosphere. They are westerlies that are faster than normal westerlies. And the reason that they are faster is because they are in a very tight pressure gradient, and that is marked by a very profound dip in temperature. So that's what we were talking about before in regards to the upper levels and why they horizontally still maintain pressure gradients, and those pressure gradients become tighter when there is a dramatic drop in temperature in the upper levels. In the polar cell, this change in temperature is due to converging warm and cold air. And we need to look at that to understand what we're talking about in regards to a jet stream. So let's look at it a little bit deeper. We know that the warm air is from the warming that is relative at the 60-degree parallel. It's far up north. 60-degree parallel is up around Montreal in Quebec for us. And those areas can get they stay cool during the summer. They get very cold during the winter. Relatively, though, these areas, especially along the coastlines, can be warmed by ocean currents. And certainly they are going to be warmer than the poles that are up even farther north, obviously. So in terms of that, we have areas along here that are lifting because they have relatively warm air at the 60s. And this is actually this cool, cold, relatively, air that has warmed in the 60s is met by a remnant of the Hadley cell. The Hadley cell is sinking air that hit the surface and diverged, and part of the diversion went north. Part of the diversion went south. But part of this diversion went north. It's been compressionally warmed. This is very warm area around the 30s. Remember, this is desert air. We remember around the 30s, very warm air. And it is now moving northward toward the cold air at the surface, relatively, at 60 degrees. So you have these two divergent temperatures that are convergently lifted in this area because there's nowhere for them to go. They meet, and the only place for them to go is up. It's a convergent lift area there with a profound difference in temperature. With this profound difference in temperature and that pressure gradient force, it causes winds in the 60s. And in fact, in the southern hemisphere, the 60-degree parallel is known as the screaming 60s. And part of the reason it's known as the screaming 60s is because there is so much water in the southern hemisphere. The oceans are so much larger, so much less land, that you really almost have a model of the three-cell model that says there's only water on Earth. There's so much flow in that area, and that area can warm so effectively with the ocean currents of the 60s that it produces this dramatic temperature gradient that calls for some of the roughest oceans in the world at the screaming 60s. So, in fact, cruise liners can only go down there for about 2 to 3 weeks in January, which is their summer, because at any other time of the year, the cruise ships cannot handle the seas around the Cape of Good Hope. So that gives you an idea of what it's like to be sailing in those areas of the southern hemisphere in the 60s. For us, we have more land in the area, but the 60-degree parallel is always known for rough storms. Nothing quite like the southern hemisphere, though. Let's give that horizontal view of the horizontal pressure gradient and the pressure gradient force. Just a reminder here, you are seeing the surface of the cold air coming out of Canada. You are seeing the surface of the warm air coming out of the Gulf of Mexico. You're seeing the altitude difference between those two surfaces on the 500 millibar chart. All right? When you are looking at the horizontal movement of air, you will see that if I started here, way back on the 500 millibar level, and moved horizontally, I would have a ways to go before I got into the 300 millibar area. Probably the 300 millibar is around here. And I would have quite a ways to go, a gradual movement from the 500 millibars to get to the 300 millibars. That gradual movement is a sign that, yes, you need to seek equilibrium, but it's not a mad rush because you have a broad area between 500 and 300. It's like the broad pond where there's not much current in the pond. Alternately, when you get closer to the temperature gradient, you are running into the 300 millibar level without much space there. This area here is a tight pressure gradient caused by a drop in temperature. In that area, there's such a difference between the 500 and the 300 millibars that this is going to reach equilibrium very rapidly. It's such a difference, it wants to move rapidly. In moving rapidly, there's a rapid movement of the pressure gradient force from south to north. And in moving rapidly, and a fast pressure gradient wind keys in a faster Coriolis force that will whip that and deflect that all the way to the right and result in the westerly wind. So you can see how these jet streams can form on pressure gradients by a combination of tight pressure gradient forces and high-speed Coriolis effects deflecting to the right. I wanted to point out to you that sometimes this polar jet can easily, during the winter, reach 250 miles an hour. And in fact, pilots who are flying from San Francisco to New York will often go north near the 60s to try to catch the jet stream, and oftentimes the jet stream in the winter will come a little farther south because of all the cold air coming out of the poles. But the pilots definitely know where the jet stream is, how high they have to go to get it, where they need to go to get it, and then they ride it to New York. And it takes about 45 minutes, sometimes an hour off the trip, because the jet stream is just pushing them so much faster, it can easily get up to 250 miles an hour. I saw it in January, I think up to 238 miles an hour. Really incredible. Now, there is, like I mentioned, there's a 250 mile an hour, and I wanted to show you an example currently of what's happening. This is the jet stream and some forest fires out west that have gotten caught up in the jet stream. This is all the west here. Here is Canada up here. Okay, these are the Rockies. There's the Great Basin in Nevada. The western fires are getting caught up in the jet stream and moving right on the jet stream up into the northeast. So we often get the soot from the fires through there on the polar jet stream that has moved a bit north in the winter. And conversely, I wanted to let you know that there's another jet stream, and that's called the Subtropical Jet stream. This is a jet stream that evolves out of the remnants of the Hadley cell. And so it's a bit different right here. This jet stream is formed just by the sinking air of the Hadley cell and the force of the sinking air. Because remember, we have very warm air coming out of the equator, that is cooling in the upper atmosphere and eventually sinking down. And it's gaining quite a bit of force as it sinks because of that compressional warming. But there's no convergent lift here. This is not as strong a jet. That said, there are times when the subtropical jet can be very effective, and that's usually seasonally. In the winter time, there can be cold surfaces at the 30-degree mark, right around Jacksonville, Florida, as we said, right around Tucson, Arizona. You can get some troughs coming out of Canada, which really chill the ground at those levels and chill the atmosphere at those levels. In that case, you will have a difference between the warm air coming out of the Hadley cell and what could be coming in from Canada to chill this area. In that case, with those temperature gradients, you could have a faster subtropical jet in there because of the pressure gradients. Conversely, in the spring, when there is warmer air coming out of the equator, you can also have that with the differential from cool air that's still coming out of Canada. So there are seasonal issues. During the summer, the subtropical jet stream is not that important. It's relatively weak as the polar front moves north with the cold air moving north and all of the warm air moving and pushing it along. At maximum, during the seasonal times, during the winter and spring, this jet stream will get to 60 or 70 miles an hour. That said, it's still important, and I wanted to give you a shot of a beautiful shot that is in July right now, showing the jet stream, the polar jet stream up north, and this beautiful subtropical jet stream that you see in here that is low, right around the 30s, Jacksonville, Florida, right there. It's right at the 30s. And so this gives you an idea that the subtropical jet stream is weaker, but it still exists, and it's still a force. We talked about the southern hemisphere. Now we're going to go back and explore the southern hemisphere a bit. What I did is I just flipped the other graphic that I had, because it's a great graphic and because the flip represents the southern hemisphere. Here's the equator flipped around. Here's the 30-degree south mark flipped around, 60-degree south mark. Down here is the South Pole. The same thing happens in the southern hemisphere. You have a thermally driven polar cell right here. And it is thermally driven from the 60s and the heating in the 60s, especially because they have more ocean and they maintain their temperature in a much more temperate area with the ocean around. Remember, the ocean warms more slowly and cools more slowly. So you can think about convergent lift in this area with the warm air diverging from the bottom of the Hadley cell and moving toward the cold air at the 60s. You can have convergent lift here. When you have convergent lift, it'll rise up, and then in the southern hemisphere, the Coriolis deflects to the left, and in deflecting to the left, you actually have a westerly wind that moves easterly. So you have westerly prevailing upper level winds in both the northern and the southern hemisphere, even though the Coriolis tilts in opposite ways and deflects in opposite ways. Please keep this in your head and think about what you're looking at here, because this is logic that you might have to go through again and again. So for the jet streams in the southern hemisphere, they rise up, and as they rise up, they are deflected to the left, which makes them a westerly to easterly wind. Those are at 60 degrees south. You also have a subtropical jet for the same reasons as the northern hemisphere subtropical jet, that It is a weaker area in the 30s that is really only based